welcome back. Or if it's your first time watching, welcome. In my experience, students have a tendency of finding truth trees to be a bit tricky. And the reason for that is they're a bit tricky. So let's talk about truth trees. In this video, I'm only going to cover an introduction to this subject. There are three things that I want to teach you about truth trees. One, what their structure is. Two, what their purpose is. And three, what it is that makes them valuable. I'll provide you with the rules and some examples in a future video. But before you run off to watch that video instead, I still recommend watching this video in its entirety. It's tempting to just run off and try to memorize the rules to then go and solve some truth trees and get your homework over with. But I promise you that understanding truth trees properly will be super helpful, especially later on. All right, so let's begin with the structure of truth trees. Truth trees begin with a single branch. This is the trunk of the tree. On either side of that branch, we can place statements. The left side of the branch represents true, and the right side of the branch represents false. So if we have a statement on the left side of this branch, then that means that that statement is true. And if we have a statement on the right side of the branch, then that statement is false. Now, if you're wondering why you would put a statement on the left rather than the right, don't worry about that just yet. We'll get to that. For now, what matters is just knowing that putting statements on the left makes them true, putting statements on the right makes them false. All right, so we know what each side of the branch represents, but obviously there's more to truth trees than just this one line. Truth trees have an annoying habit of having many branches. So naturally that raises the question, what causes a branch to split? To answer this question, you need to know that the job of a truth tree is just to decompose compound statements into, eventually, atomic statements, according to some rules. The rules, which I'll cover in the next video, tell us exactly how to break down those compound statements. And sometimes breaking down these compound statements requires that we split the branches of a truth tree. As an example, if we have a disjunction on the left side of a branch, then when we decompose that disjunction, we would end up with a truth tree that looks like this. Why? Well, this is just how the rules tell us to break down disjunctions. Right now, you don't need to memorize this. Let's just talk through what happened. First, remember, as we just covered, that placing a statement on the left side of the truth tree means that it's true. So in this case, we're saying that this disjunction is true. As you'll remember from your truth tables, disjunctions are true when either disjunct is true. Since we know that the disjunction P or R is true, then we also know that either P is true or R is true, although we don't know which. And that's why we split the branch. Each new branch, in this particular case, just represents a different way that the disjunction could turn out to be true. Notice, and this is important, that we placed P on the left side of its branch, and we placed R on the left side of its branch. The left side of every branch represents truth, and the right side of every branch represents false. Since disjunctions are true when either disjunct is true, we simply place these statements on the left side of their respective branches. You might wonder why we didn't create a third branch that has both of them on the left side, given that, of course, disjunctions can be true when both disjuncts are true as well. There's a good reason that we don't make a third branch, but it's just not worth covering in this video. I promise that I'll talk about it in the video where I cover the rules. For now, just take my word for it that splitting this branch in this way covers all of the possibilities that matter. Now, decomposition will not always result in branching. If, for instance, we have a disjunction on the right side of the branch, then the rules will tell us that we should draw the truth tree like this. And this honestly makes a lot of sense. There's more than one way for a disjunction to be true, but there's only one way for it to be false, and that's for both of the disjuncts to be false. And that's the only thing that this truth tree is telling us right here. Since P or R is false, then it must be the case that P is false and that R is false. And so we just place both decomposed statements on the right side on the same branch. Okay, if you're finding this a bit tricky already, don't stress it. Right now, what matters is that you understand what splitting the branches of a truth tree means. When there's more than one way for a compound statement to be true, or more than one way for it to be false, then we split the branch. If there's only one way, then we don't split the branch. As for when we should split, the rules will tell us that. All right, so there's one more thing you need to know about the structure of truth trees. You need to know what it means for a path to be open or to be closed. Okay, so what is a path? If you start at the very bottom of the tree and you draw a line up the branches all the way to the very top of the tree, what you get is a path. Each path on the truth tree represents a possibility, a way things could have been. On the truth tree, with our disjunction on the right, there's only one path. We never had to split anything. But on the truth tree, with our disjunction on the left, we have two paths. The path on the left represents the world in which P is true and the disjunction P or R is true. And the branch on the right represents the world in which R is true and the disjunction P or R is true. Notice that these are the only two paths on this tree. Paths have to move from the bottom of the tree all the way to the top. They cannot turn around. I don't know if the camera or the microphone is getting this, but man, it is coming down outside. All right, so with all of that in mind, let's talk about what it means for a path to be closed off. A path gets closed off, and X gets placed at the very bottom when that path has a contradiction. Every path, as I said earlier, represents a possibility. But contradictions, as we know, are impossible. In this slightly more complex truth tree, and really, don't worry about how we got to this truth tree, you'll notice that P appears on the left here, and it appears on the right here. That means that on this one path, P is both true and not true. That's impossible, and so we close off this path. When a path gets closed off, you do not decompose anything under it. That path is closed. It is out of commission. Do not use it. Stay on the lookout for contradictions as you build your truth tree. The second you spot one, you need to close off that path. Now, if a path does not contain any contradictions and there's nothing left to decompose, then and only then you mark it with a circle to represent that it is open. That's just a way of expressing that that path has no contradictions. It is a live possibility. All right, that's everything you need to know about the structure of truth trees. To recap, everything on the left of a branch is true, and everything on the right of a branch is false. Paths represent possibilities, and they run from the very bottom of a tree all the way to the very top. An X at the bottom of a path represents that that path contains a contradiction and is not a real option. Whereas, on the other hand, a circle at the bottom of a path represents that that is a real option. It's a real live possibility. There are no contradictions on that path. Circles get placed only when there are no statements left to decompose. Okay, and with that, let's go ahead and move on to talking about the purpose of truth trees. All right, so what exactly is the point of a truth tree? What is it that truth trees are supposed to do? In answering this question, I'm going to compare truth trees to truth tables, with which you should already be familiar. So truth trees and truth tables both represent possibilities. Truth tables have their rows. Each row represents a possibility, a way that things could have been. Truth trees, just like truth tables, also represent possibilities. Only rather than having rows, what they have are paths. Each path in the truth tree is a way the world could have been. Unless, of course, the path ends in an X. If a path ends in an X, then we know that that path contains a contradiction, and so it's not a real possibility. Another similarity between truth trees and truth tables is that both can be used to test arguments for validity, to test whether a statement is a tautology, to test whether a set of statements is consistent, and on and on. Both can be used to test for all of the same things. And I'll be uploading videos in the future teaching you exactly how to use truth trees to test for all of these things. But that is where the similarities end. Truth trees and truth tables are actually really different. The main difference boils down to this. Truth tables are bottom up, but truth trees are top down. All right, so what does that mean? Think about how you construct a truth table. You start by assigning truth values to the atomic statements, and then you go ahead and you evaluate compound statements on the basis of those values and how the logical operator evaluates those values. So, in a truth table, if you have a row in which, let's say, P is true and Q is false, then you'll know that the conjunction of P and Q will evaluate to false. But truth trees work the other way around. When you first write up your truth tree, The first step is to place statements on either the left or the right of the main branch. So right off the bat, you're assigning truth values to compound statements. Placing a statement on the left, like I said earlier, just means that it's true, and placing it on the right just means that it's false. Then, according to some rules, you decompose those statements. Ultimately, you'll decompose them until all you're left with are atomic statements. So, unlike with truth tables, when you're working with truth trees, you start by assigning truth values to compound statements, and then you decompose all the way down until you get the truth values of the atomic statements. Literally the opposite direction. All right, so at this point you might be wondering, how do you determine where to place a compound statement at the beginning of the truth tree? That's a great question. The answer is that it depends on what you want to do with your truth tree. Whether you'll place statements on the left or the right or both just depends on whether you want to test for, let's say, whether an argument is valid. Or maybe you want to test whether a set of statements is consistent. It just depends. And this gets us to the main purpose of a truth tree. The main purpose of a truth tree, its primary function, is to tell you whether the original truth value assignment that you made at the beginning of the truth tree is actually possible. Remember how you place an X at the bottom of a path when that path contains contradictions? This is where the magic of truth trees comes into play. If, by the time you're finished building your truth tree, every single path ends up with an X, so all of the paths are closed, they all contain contradictions, then what you've learned is that the way that you arranged your statements at the very beginning of the truth tree on the trunk, that arrangement is not possible. Just as an example, if I were to start by placing all of my compound statements on the left side of the main branch, and all of the paths end up closing, then what I've learned is that it's not possible for all of those statements to be true at the same time. If, however, so much as a single path on the truth tree remains open, then you know that those 3 statements or 4 statements or however many statements that you placed on the left of the main branch, you know that they can all be true at the same time. And it's this feature of truth trees that allows them to test for things like validity, or consistency, or tautology, or contradiction, or whatever else. If you want to test whether a set of statements is consistent, just place them all on the left side of the branch. If all of the branches close, you know that they're inconsistent. If there's a branch that remains open, you know that they're consistent. Want to test for validity? Place all of the premises on the left side of the branch, and place the conclusion on the right side of the branch. If they all close, you know the argument is valid. If a single path stays open or more, then you know that the argument is invalid. Don't worry about memorizing any of this. I'll upload videos specifically to teach you how to use truth trees for all of these things. Okay, so I know that is a lot of information. Here's what you absolutely need to know at this point in the video. The left side of any branch on a truth tree represents true. The right side represents false. Branches split when there's more than one way for the statement that you're decomposing to be true or false. We have not covered how to decompose statements. A path closes when it has a contradiction. If you've decomposed all of your statements and you still have a path without any contradictions, then that path gets a circle. It remains open. And finally, and most importantly, truth trees tell you one and only one thing when they're complete. They tell you whether your original set of truth values is actually possible. That's it. They don't tell you anything else. If all of the paths close, then you know that your original truth value assignment is impossible. If, on the other hand, even so much as one path remains open, then you know that your original truth value assignment is possible. And that is the main purpose of a truth tree. Okay, one last thing. I said earlier that truth trees and truth tables can all be used to do the same things. You might be wondering at this point why on earth you need to learn truth trees when you already have truth tables. They can do all of the same things, and truth trees are so much more annoying and complicated than truth tables are. What exactly is the value of a truth tree? Why are we learning this? In statement logic, when you're testing for validity and such, it actually is probably a better idea to just stick to truth tables. They're easier, they're simpler, they're more straightforward. And, of course, importantly, they get the job done. However, where truth trees really shine is in predicate logic. which for many students you'll be learning later on in the semester in an introductory logic course. In predicate logic, truth tables are borderline unusable. Seriously, they're just awful. Truth trees, on the other hand, handle predicate logic with ease, but they're worth learning right now. Trust me, you don't want to be learning truth trees and predicate logic at the same time. Okay, that's everything that I wanted to cover in this video. I know truth trees are a pain, so I'm going to upload videos to cover everything you could possibly care to know about truth trees, and probably some stuff that you couldn't care to know about truth trees. I'll be covering everything. Thank you for watching this video. If you want more content about logic or philosophy more generally, you should consider subscribing. I'll see you next time.